Hi there, we are the Firefighters, Michael and Kun from Computer Science. We will now present our hacking on the wildfire. So first we will introduce the dataset and go through some results in exploratory data analysis. After that, the problem will be set up. Kun and I will present two different approaches, the two ways we used to tackle the problem. And finally, the results and the forecasting will be discussed. So we are provided with 5 kinds of data, including the daytime, land cover, latitude, longitude, meteorology observations, and most importantly, the verse observation. So the verse observation is the binarized intensity of infrared radiation from the ground, and positive pixel may suggest the fire is burning at the corresponding area. So these two in below are two examples of the verse observation. So our objective is to forecast the most likely verse observation in the plus 12 hour and plus 24 hour. As you can see in the verse observations, most of the pixels are 0, which means most of the areas are not burning. So this will actually lead to a class imbalance problem that we will address using the class weights multiplied to the loss function to compensate. The problem can be set up as pixel-to-pixel classification. What we need to predict is two binarized images representing the verse observation from the other input features, including the daytime, land cover, and the meteorology observation, and of course the previous verse observations. So now I will talk about the deep Markov model. We are extending the regular hidden Markov model to model the temporal dynamics of the wildfire. So the plan is to encode each of the verse observation into a 50 dimension latent space using the Bayesian approach. So conventionally, we can use Kalman filter, for example, to model the dynamics of the latent space in linear. But in this project, we will be using a neural network, which is a nonlinear model, to describe how the wildfire would progress throughout the time. So using this model, it's also gives us good flexibility to incorporate, for example, the land cover or the meteorological observation to the model in a interpretable manner. We will be using totally 3 neural networks to model the emission, which is the latent space, the translation from latent space to the observation, and the transition, the probability between two latent space, and another neural network to model the posterior probability, which is an estimate of the latent space provided a sequence of observation. The objective is to predict the 2D trajectory of wildfire on a low-dimensional manifold. So the 6x6 matrix on the left are 36 samples of the wildfire progressing in its latent space. As you can see, if we can describe the dynamics of the wildfire in that 2D latent space, we can explain in which conditions that the wildfire would extinguish, and in which conditions the wildfire would grow out of control.
In this deep learning method, we frame the problem as image-to-image translation with different input and output channels. Particularly, we investigate the conditional adversarial networks. We condition the model to predict the corresponding targets. Two models are trained simultaneously by an adversarial process. The model has the input size of 32 by 30 by 30, where the channels come from the observed land cover and meteorology features. The architecture of the generator is an encoder-decoder network. The input is passed through a series of layers that progressively downsample until a bottleneck layer, at which point the process is reserved. To give the generator a means to circumvent the bottleneck of information flow, we add skip connections following the general shape of the U-net. For a discriminator, since our problem focuses on pixel-wise precision, we aim to restrict the GAN discriminator to only model high-frequency structure. Therefore, we apply the discriminator architecture of batch gain that only banalize structure at the scale of batches. This square loss of gains and binary cross entropy loss of the pixel-wise loss is combined for the optimization process. See, the mean square error of both the models is very low. Note that because of the imbalance problem, MSE is not a really good metric. So we also compare the intersection over union. We can see that the gain has a better IOU.
So now we can look at the t-SNE plot of the dataset. So I've conditioned the dataset into the day group and the night group. So if we look at either one of these groups, we can see in each of the time steps a big cluster around some location, and that cluster actually represents the samples with little or no fires detected. The t-SNE plot gives us insights that we could potentially add a factor that separates different intensities of fire, so the model can focus more on the groups, on the samples which actually have a progressing wildfire. Other than that, we can see the samples which actually have fire can be clustered into different small groups. The next step of us will be identifying in an unsupervised manner that what these groups are supposed to mean and how the progression of these small clusters are relevant to the other observations, say the meteorological observation. So how does the wind and the land cover affect the movement of a sample between cluster to cluster throughout the time?
Here we can see the prediction of the two models. The GAN method shows a better ability to predict high-frequency structure at the pixel level, while the DMM method gives blurry prediction and is not accurate at 24-hour target. We attribute this to the architectural complexity and being easier to train on the deep learning model. In contrast, the graphical model is more structured and better at explaining counterfactuals, but harder to train due to the need of domain knowledge to define the optimal HMM. In the future work, we will focus on better tuning the deep Markov model and investigating on combining the advantages of the two models.